ALSCO Limited provides a wide range of products for electrochemistry and spectroelectrochemistry applications, including bipotentiostat, rotating ring disc electrode apparatus and spectrometer system. We also deal in various types of spectroelectrochemical cells, electrodes, and accessories for electrochemical measurement. BAS Incorporated is an exclusive distributor of ALSCO Limited products. Where are ALSCO Limited and BAS Incorporated located? ALSCO Limited and BAS Incorporated are Japanese company, located in the center of Japan, in Tokyo, Sumida Ward. Close to the Tokyo Landmark Tower, Tokyo Sky Tree. We will quickly introduce you the ALSCO Limited product lineup. RRDA3A is an accurate rotator system for hydrodynamic modulation rotating ring disc voltammetry. It has corrosion resistance and compact design and easy operation. It can be operable as ride and RRDE and the rotation speed from 100 to 8000 rpm. Remote and manual control of the rotation and gas purge is possible. Also the spin coding of the electrode. And the speed and purge time can be displayed on the LCD display. It is precisely controlled by pulse width modulation. Electrodes are small and rapidly interchangeable. The unit also provides an adjustable valve system for inert gas purging inside the cell vial. The SEC 2020 spectrometer system is a spectrometer that enables various spectrometric measurements, focusing on spectroelectrochemical measurements. The high-performance grading and optical design makes possible to measure with high sensitivity in a wide wavelength range, from ultraviolet to near-infrared, with a single unit. For the light source, a compact modularized deuterium halogen lamp is used, which is fixed to the cell holder on the accessory platform for the measurement. Furthermore, the spectrometer and the light source come with SMA 905 connector, which makes possible to connect various optical fibers and probes, to construct the original measurement system. ALS also provide electrodes for the basic 3-electrode electrochemical measurement method, such as working electrode. A variety of the working electrodes are available. You can choose according to you the application purpose. For the reference electrode, you can select according to the measurement requirement. A variety of the reference electrodes are available such as silver chloride for aqueous solution, silver ion for non-aqueous solution, and the mercury types are available, which includes the reference electrode for alkaline solution. For the counter electrode, you can also select the suitable one for your measurement purpose. The electrodes introduced here are for the usual static type voltammetry cell. ALS also deal in electrode lineup for flow type. Voltammetry cell for electrochemical measurement. You can select from the lineup depending on the measurement method, sample amount, and combination of electrodes. VC4 for small sample to the measured. SVC2 a multi-purpose cell. SVC3 standard voltammetry cell for 3 electrode with OD 6.0 mm. SVS3C for application at low temperature. And bulk electrolysis cell. Model 2325 is a very low price and high performance bipotentiostat based on modern semiconductor circuitry and advanced software technology. Low noise, high speed, and small space measurement were considered for the development of Model 2325. The user-friendly interface is designed for supporting wide applications. Model 2325 can be applied in various experiments, such as RRDE, sensor development and spectroelectrochemical measurements, etc. It can be not only applied for research purpose, but also for student experiments and industrial applications due to the low price and high performance. CS3A cell stand is specifically designed to use a variety of solid electrodes conveniently and cell accessories available from ALS. The working cell is enclosed in a Faraday cage to reduce external electrical interference. A built-in gas control allows purging of the sample. CS3A cell stand features are: reduce the external electrical noise, gas purge function, remote and manual controlled GAR purge and magnetic stirrer, arrows remote control from the PC trough, the potentiostat software, corrosion resistance design. Reversible hydrogen electrode set up using H2G1 portable hydrogen generator. Reversible hydrogen electrode is a kit, in which hydrogen gas is generated by electrolysis of strong acid then stored. It makes unnecessary the complicated and dangerous setup of the hydrogen cylinder and avoids the large volume of hydrogen gas exhaustion, despite that it has a good potential stability. It can be used in a strong acid solution. Also, when using double junction, it is possible to apply in a non-acid solution. Using H2G1 portable hydrogen generator, even without a potentiostat, makes easily to charge the hydrogen gas into the reversible hydrogen electrode kit, and use it as a reversible hydrogen electrode with good potential stability. The practical and safety reversible hydrogen electrode can be prepared by using this instrument for hydrogen gas generation for a reversible hydrogen electrode kit. This prepared reversible hydrogen electrode has high accuracy, stability, and can be the perfect alternative for the traditional standard hydrogen electrode. When using the reversible hydrogen electrode with a double junction chamber, makes possible to apply in a weak or neutral electrolyte solution. The prepared reversible hydrogen electrode can be used in an electrochemical measurement, such as for the RRDE measurement. As an auxiliary function, H2G1 portable hydrogen generator can be used for the potential measurement. Some additional information about BAS and ALS. For the complement of our home page, we have our YouTube channel. In the BAS channel, we have collection of the movies in English, the BAS channel collection, where you can access and watch a variety of the movies, since the product introduction, which includes the product introduction, setup, and troubleshooting, until the technical lectures in the field of electrochemistry and spectroelectrochemistry. In this opportunity, let's follow the BAS channel and watch the movies of a variety of the topics. Also, through BAS channel, the BAS Electrochemical Webinar is held online frequently. The BAS Electrochemical Webinar is an online webinar which is held frequently by BAS International Sales Team, with their invited lecturers, and it consists of lectures focusing in the field of electrochemistry and spectroelectrochemistry. Until now, a series of 7 webinar focusing in the basic and theory which was suitable for who are starting and to review and refresh the knowledge in the electrochemistry and spectroelectrochemistry field were introduced. The series of the lecture was introduced online through the YouTube's BAS channel. The announcement for the future webinar you can have in our ALS website, always on the top page, from which you can jump to the application page, where you will find the detailed information about the schedule and the theme. We are waiting you for the next webinar. For any inquiry, please feel free to contact us.
Hello everyone, thank you for attending the BAS Electrochemical Webinar 2021 Autumn. I'm Miho from International Sales Team, and I will be the moderator. Before we start, as unusual, we'll ask you, don't be worried to record and enjoy the webinar. We are recording and we will send the direction to you as soon as it is ready. In this way, you will be able to review the full webinar. Also, if you have any question, please feel free to contact us. Well, let's start today's webinar. Today, it will be the second lecture introduced by Dr. Jiang from BAS Technical Support Department. The theme is Introduction of Application Example of Spectroelectrochemistry.
Hello everyone. In this topic, I'd like to introduce some application examples of spectroelectrochemistry. Let me show you the contents we will talk about. At first, there is a quick review on what's spectroelectrochemistry, techniques on which the SEC is based are. This is also introduced in a previous lecture, BAS Electrochemical Webinar, January 2021. In the second part, I will review on the features of SEC and the strengths of this method over traditional electrochemical methods. And then, in the third part, there is a quick review of typical SEC methods that are classified into transmission method, reflection method, and excitation method according to the light incidence method. We will show you the principles and characteristics and what kind of study is suitable for each method. Optically transparent thin layer electrochemical OTTLE cell method is the most studied and used method. In the second half of the lecture, I will introduce some application examples using OTTLE cell and optical transparent electrochemical OTE cell to show what kind of research the SEC method was applied to. At last, let's look at the different roles of OTTLE and OTE cells. First, let's see what's spectroelectrochemistry. It can be abbreviated as SEC. It's a measurement which combined the spectroscopy measuring method with the electrochemical measuring method simultaneously. Techniques on which the SEC is based are electrochemistry and spectroscopy. Electrochemistry studies the interaction between electrical energy and chemical changes. This technique allows us to analyze reactions that involve electron transfer processes. Spectroscopy studies the interaction between electromagnetic radiation and matter. This figure shows the often used techniques. Ultraviolet visible absorption spectroscopy is the most well-known method, and spectroscopy is combined with electrochemistry techniques, for example, coronal amperemetry, coronal potentiometry, and voltammetry. Next, let's look at the features of SEC. The strength of this technique relies on generating spectroscopic information about in situ electron-generated species. The in situ measurement make it possible to accurately observe the status of some unstable electrochemical products or intermediates. Observing reaction on the electrode surface, the interface of an electrode and solution, and the electronic state of a molecule. Also, we can get the absorbance of a reactant, product, and mediator. From the features, we can know the advantage of SEC methods over traditional electrochemical methods. To a substance that difficult analyzed by electrochemically, the redox potential can also be computed from the absorbance if the reactants or products have spectrum characteristic. Identification of the molecular species are all possible when an electrode system is at an equilibrium situation or a stationary state. The chemical species near electrodes can be identified by absorbance and spectrum. SEC technique combines the spectroscopy and electrochemical measurement. This combination can be classified according to the type of spectroscopy. Following, we will introduce some typical SEC techniques classified according to the light incidence method, transmission method, reflection method, and excitation method. The basic cell structures were also introduced in our previous webinar. Therefore, here we only show the additional information. The basic spectroelectrochemical method is transmission method. It's performed in the ultraviolet, visible, near-infrared regions. The typical transmission method, as shown here. Light transmits the electrode. Therefore, usually, optical transparent electrode or grid electrode is used. The difference is solution thickness or optical path length. By measuring absorption spectrum of electrode reaction product using transparent and grid electrode, we can get the absorption spectrum of products and intermediates, absorption spectrum of anion and cation radicals. This transmission method was used to study, for example, the absorption characteristics of redox compounds of dyes. Optically transparent thin layer electrochemical OTTLE is the most studied and used method because of the simplicity of the experiment. We will introduce some application examples use this method. Second, reflection method is also performed in the ultraviolet, visible near-infrared regions. The typical reflection method as shown here. Light incident and reflect on the electrode surface, and is detailed by different incident light and direction. By measuring the reflected light or the reflected polarized light on the electrode surface, we can get absorption or reflection spectrum of electrode surface to know the absorbed species and deposits on the surface, the coverage and film thickness of the absorbed species and deposits on the electrode surface. This method is used for example, the study of dye adsorption behavior, metal precipitation and dissolution reaction behavior, adsorption of gas and ions on the electrode surface. Third, luminescence method. Excitation light is performed to the electrode surface or the solution. By measuring the luminescence of the system, we can know electrochemical reactions on the electrodes and changes in absorbance or luminescence related to the electrode. This method is used, for example, research on electrochemical luminescence, ECL labeled materials, or ECL reaction mechanism. Raman spectroscopy is a special method using laser light as excitation light. This method is used for study Raman spectrum of adsorbed species and deposits on the electrode surface. This method is for advanced users who are familiar with Raman spectrum. Ultraviolet, visible, near-infrared absorption using optically transparent thin-layer electrochemical OTTLE method is the most widely studied and theoretically explained method. Following, we will introduce some SEC applications examples to help you understanding what kind of research the SEC method was used for. The first and second example used OTTLE cell and ultraviolet visible absorption method. The third example used a conventional OTE cell and ultraviolet visible absorption method. The fourth example used OTE cell and absorbance electroluminescence method. The first example is a spectral potential static technique for determining formal reduction potentials and the number of reaction electrons of redox couples. The measurement of formal reduction potentials and the electron transfer stoichiometrics N values is a significant aspect of these investigations. Many biological species, such as cytochromes and ferredoxins, undergo heterogeneous electron transfer very slowly or irreversibly. Such behavior is usually due to severe adsorption of the biocomponents or to insolution of the redox center from the electrode by the surrounding protein structure. These biological species are difficult to study by conventional electrochemical methods such as cyclic voltammetry. The cyclic voltammogram in Figure 4 illustrates the extent of irreversibility for cytochrome C at a gold minigrade in the OTTLE. Spectroelectrochemical techniques based on mediated titrant have been developed and effectively used to measure the formal reduction potentials and N values for biological systems. Here is the next equation shows a relationship between cell potential and concentration of the ions. EAPPL is applied potential, E is formal reduction potential, O is concentration of the oxidized species, R is concentration of the reduced species. E and N are determined from a nuanced plot of the values for applied potential and the corresponding values of O divided R. The basis of the technique is control of the ratio O divided R of the redox couple. O divided R was determined from the spectrum recorded from its potential, like left figure. UV visible absorption was the main optic technique used in conjunction with OTTLE. Spectra for cytochemistry for a series of applied potentials are shown in Figure 5. The cytochrome is fully oxidized at 300 mV and fully reduced at minus 600 mV. In this case, about 10 minutes was required to achieve equilibrium after a potential change. Therefore, a thin layer is required to reduce the time. In this example, E and N are determined from plot of the values from EAPPL and the corresponding values of log O divided R. Typical nest plots for cytochemistry at various temperatures are shown in Figure 6. Values of E equal to 62 plus minus 1 mV and N equal 1 are obtained from the intercept and slope respectively at 25 centigrade. Thus, very precise values of formal reduction potential can be obtained for a biological redox system that essentially is electrochemical irreversible at a gold electrode. For a detailed principle explanation, please also refer to our website. SEC method can be used for study of a very slow heterogeneous electron transfer and homogeneous chemical reactions. The rate of the electron transfer in the first one electron step is unusually slow in the reduction of vitamin B12. The polarographic and cyclic voltammetric studies didn't indicate any discernible, but it can be easily studied by thin layer spectroelectrochemistry. Potential static curves for the reduction of B12 is measured using the OTTLE with mini-grid electrode. Absorbance at different potential were performed at first. Curve 1 at 0 volt is a typical spectrum for B12, a curve 3 element, with characteristic peaks at 520 and 550 nanometer. The curve 2 is at minus 0.6 volt, decrease in the 520 and 550 nanometer peaks, and the development of a new peak at 475 nanometer. This peak is typical of that reported for B12R, a curve 2 element. The curve 3 at minus 0.66 volt completely converted to a curve 2 element. The curve 4 is at minus 1.0 volt for B12S, a curve 1 element with a weakly absorbing broad peak at 560 nanometer and a tapered soldier in the region of 460 nanometer. The quantitative change in the typical peak absorbance values as a function of applied potential for vitamin B12 is monitored then to study the detailed redox mechanism. From the potential absorbance curves at respective peak It is known that the B12 is totally reduced to a curved 2-element over a relatively narrow potential range. However, reoxidation occurs in a broader range. This research showed that, in spite of the fact that the electrokinetic data are very complicated, unusual, and virtually impossible to interpret mechanistically, and optical monitoring of the solution composition using the OTTLE technique gives a good picture of the net or overall redox reactions that take place. The third example is analysis of complex order of charge transfer using optical transparent electrode method. As a classic example, mixture of cytochrome C oxidase and cytochrome C was used as a sample. The experiment was a colorimetric titration by the radical cation of methylviologen. Absorbance was recorded during equal incremental addition of reductive titrants. The intensity of the 605 nanometer band of the oxidase changes during the initial and final portions of the titration. The intensity of the 550 nanometer band of cytochrome C changes predominantly during the intermediate stages. It means one of the heme in the 2-cytochrome oxidase is reduced first. Then monovalent cation of methylviologen reduces the heme in cytochrome C before it deals with the second heme of oxidase. Charge distribution among the heme components in mixtures of these two redox enzymes was evaluated by monitoring the absorbance changes at 605 and 550 nanometers. In Figure 2, left figure shows the absorbance changes at 605 nanometer and 550 nanometer during reduction cycle by monovalent cation of methylviologen. Right figure shows the absorbance changes during oxidation by O2. It is evident that the oxidative curve of the 605 nanometer band of cytochrome oxidase is not a mirror image of the reductive curve. Differences in the pathway of the electron transfer process during a reduction cycle as compared to an oxidation cycle are indicated by variation found in the absorbance behavior of the heme components. This experiment was a very good example of indirect electrochemical measurements, especially applications to biopolymer enzymes, because they may not directly cause charge changes at the electrodes. SEC method can visualize the electrode processes. Here show you the study of spectroelectrochemistry of electrochromic and electroluminescent substances with screen-printed electrodes and with an optic transparent platinum mesh electrode. Various kinds of cell and optical methods were used in this paper. Figure 3 in this paper is absorption spectra of methylviologen at two different potentials. A thin film absorption cell with a platinum mesh working electrode was used. Figure 3 indicates that the change of the spectrum around 350 to 400 nanometers and around 600 nanometer can be suitable for measuring the change in absorption of monovalent cation of methylviologen as a function of the applied voltage. We can know that 600 nanometer is the typical wavelength of methyl halogen. Figure 4 shows voltammogram and derivative absorbance at 600 nanometers using specular reflection transmission cell with screen-printed electrodes. The absorbance change observed with the CV measurement. The absorbance increases at about minus 0.7 volt, the beginning of the first reduction of divalent cation to monovalent cation. At lower potentials, divalent cation is consumed, followed by a decrease in the absorbance. At about minus 1.6 volt, in the comproportionation reaction 3, the absorbance of monovalent cation increases. In the reversed scheme beginning at minus 1.25 volt, the absorbance increases continuously by reaction 4. At about minus 0.7 volt, the blue monovalent cation of methyl halogen oxidizes to the colorless divalent cation and the absorbance decreases. The derivative absorbance could easily be calculated with using Excel, gives more details. In this presentation, the variation in the absorbance is highlighted much better, and the correlation between CV and absorbance change is more obvious. Figure 8 shows cyclic voltagram and the luminescence variation of trace bipyridine ruthenium at 600 nanometers. Conventional OTE cell for absorption electroluminescence measurement was used. Solid line is cyclic voltagram and dotted line is derivative luminescence spectrum. At 0.83 volt, the oxidation of trace bipyridine ruthenium occurs and the luminescence decreases. The spectroelectrochemical measurement of electrochromic and electroluminescent substances shows a strong correlation between electrochemical reactions on electrodes and changes in absorbance or luminescence near the electrode. The research shows us that the SEC is a very powerful technique to observe electrochemical and optical changes at the electrode. In addition, the empirically observed didactical problems of misunderstanding electrochemical electrode reactions can be overcome by visualizing the electrode processes in spectroelectrochemical measurements. In above application examples, the optical transparent thin layer electrochemical OTTLE cell and optical transparent electrochemical OTE cell were used. Then let's look at the different roles of these two types of cells. The first and second example used OTTLE cells. An easily constructed OTTLE is the gold mini-grid sandwiched between two microscope slides with Teflon tape spacers, as shown in right figure. The thickness of thin layer cell is typically less than 0.3 mm. Complete electrolysis of electroactive species occurs rapidly as a result of the short diffusion path within the thin solution layer. This feature enables rapid conversion of redox couple oxidation states throughout the thin layer by appropriate potential control of the working electrode. The application of nernst plot described here are all based on this feature of rapid and complete electrolysis with a thin layer. Example 4.1. Spectra of cytochrome C were recorded under conditions of equilibrium. About 10 minutes were required to achieve equilibrium after a potential change. This time is dependent on the mediator titration concentration and the OTTLE design. Therefore, we can now, for complete electrolysis applications, a thin layer is required. Example 4.2. Spectra for the reduction of vitamin B12 were measured at various applied potentials. For such slow reaction, it's recommended to use a thin layer to get complete electrolysis or equilibrium state. Example 4.3. Absorbance of cytochrome C and cytochrome C oxidase mixture was recorded during equal incremental additions of reductive titrant. In this research, an OTE cell was used. Spectral changes at 550 nanometers was about 0.7 AU. Conventional OTE cells can be used for such titration reactions and applications with above spectral changes. Example 4.4. In order to get information about the absorption spectrum of monovalent cation of methylviologene, a thin film absorption cell with a platinum mesh working electrode was used. The bulk solution still contains unreduced divalent cation methylviologene and the absorbance around 255 nanometers doesn't completely vanish. Conventional OTE cells can be used for such qualitative measurements and applications with obvious spectral changes. The luminescence variation of trace bipyridine ruthenium at 600 nanometer was measured. A conventional OTE cell was used. Conventional OTE cells can be used for such luminescence measurements and applications with obvious spectral changes. Okay, let me summarize today's lecture. Spectroelectrochemical methods have unique advantages over conventional electrochemical methods. In this lecture, we introduced some application examples using OTTLE cell and OTE cell. The SEC method can be used for determination of the formal redox potentials and N value, study of redox mechanism, indirect electrochemical measurements, etc. We hope it will be a hint for your research. Spectroelectrochemistry becomes increasingly important as an analytical method. SEC is a very powerful technique to observe electrochemical and optical changes at the electrode. In the future webinar, we will introduce several applications using our ALS spectroelectrochemical cell and spectrometer system. Thank you for your attention.
Thank you, Dr. Jan. I wish you enjoyed the lecture. If you have any question regarding to the lecture or other topics, please feel free to contact us. The email is here. Also, we will send in the direction to watch and review this webinar. Also, the movies of a variety of topics you can watch here in the BAS channel, which you can follow and have access to the latest news, including the past webinars. The next webinar we are working out to have for December. For today, thank you again and stay safe and healthy.